Hey, so let's cover 3.5. I'm going to go as fast as I can through this because honestly, it's going to be long enough as it is. So bear with me. If I go too fast, you can always change your speed that you're listening to me in. Or if I'm going too slow, you can do the same. All right, blank, blank. So this is just vertical shift. Vertical shift means moving the graph up or down. So taking the original function f and shifting it up if it's +1 or down if it subtracts something. So given a function f, you're going to have a new function g of x that's equal to the original function plus, in this case, they're doing +1. K is a constant. It cannot have an x in it. It has to be just a number. Okay, and it causes the vertical shift either up or down. The graph will shift up when K is positive. When that constant is positive, the graph will shift down when it is negative. Oh, pardon me, throat's hurting. Okay, this one is not going to be on the exam, but it's just to help you see what's happening with vertical shifting. So regulating temperature in a green building, the airflow vents near the roof open and close throughout the day. The graph below shows the area of open vents V in square feet throughout the day in hours after midnight, which they're calling T. During the summer, the facilities manager decides to better regulate temperature by increasing the amount of open vents by 20 square feet, so by the area throughout the day. At night, a day and night, sorry, sketch a graph of this new function. Well, I didn't sketch it. I just pulled it in because I can't sketch it this nicely. So let me show you how this works. All right, the original function is this one here. This is going to be our V of t. All right, this should make it a little bit darker for you. The new one is a vertical shift. So it has to do with down here is time, over here is area. And he's increasing the area, and you know time is always on the independent variable, which would be along your x-axis. So the area has to increase, which means this is a vertical shift. So from the original, he is now increasing it by 20. And everything else is going to stay the same in the time aspect of it, but the square footage of the area is going to increase by 20 square feet. Okay, that is a vertical shift. So if we took V of t as the original function, we're going to need to have a different one. So if this one over here is V of t. So we're going to need a different one, this new pink one. Let's just say G of t is equal to V of t, the original function, plus 20. That is what a vertical shift looks like. The plus 20 is going to show that it's actually shifting up. And that has to be the constant outside of the function. All right. Now we're going to shift a tabular function vertically. So we're given a x, 2, 4, 6, 8. We're going to be using this exact table quite a bit. And we're given the function f of x is 1, 3, 7, and 11. So the base function's f, and we're going to create a table for the new function g of x, which is going to take f of x and subtract 3. All right. So we're going to come down here. They just took the same table we have here and moved it here. I'm going to rewrite that it's g of x, which is our new one, is equal to f of x minus 3. Okay. So we've got the original function right here. The original x is here. Now g of x is just telling us that f of x is equal to 3. Well, if we're looking at g of 2, g of 2 is going to equal f of 2 minus 3. Okay, this is probably a little bit better than what we did in class. And so now g of 2 is equal to, well, f of 2 is 1 minus 3 is -2. -2. We're going to do the same thing for the other 3 numbers. G of 4, let's give myself some space here, is equal to f of 4 minus 3. F of 4 is 3, minus 3 is 0. All right, now we'll do g of 6. That's equal to f of 6 minus 3. F of 6 is 7, minus 3 is 4. And the last one is g of 8 is equal to f of 8 minus 3. F of 8 is 11, minus 3 is 8. And there is our vertical tabular function. It's shifting vertically. Next victim, a horizontal shift. Shift means moving the graph left or right from the original function. All right, so given an original function f, a new function g, which we've got right here, is a horizontal shift of f of x minus h. Okay, with the vertical shift, there was an outside constant. With a horizontal shift, the constant's going to be on the inside of that f original function, okay, whatever the original function is with the x. So for this one, g of x, the new function, which is what this one is here, g of x is equal to f of x plus 1. Well, in this case, they're doing g of x is equal to f of x minus h. This is f plus 1 is the vertical shift. They're not even horizontally shifting this one, so it doesn't even matter why. I'm so confused why they're actually using this. Anyways, let's keep going. G of x is equal to f of x minus h. H is a constant and it causes a horizontal shift. So now we have g of x based on the vertical and the horizontal shifts. We are now up to f of x minus h plus k. That's what I've given you so far up to now. The graph will shift to the right if h is positive. It will shift to the left if h is negative. Okay. All right, adding a constant to an input. So we're going back to that manufacturing warehouse where the facilities manager is now deciding that the original venting plan starts too late and he wants to, or she wants to begin the entire venting program 2 hours earlier. Okay, and it says sketch a graph of the new function. So this is back to the original function prior to increasing his square footage or their square footage. So let's go back. This is the original. Okay, and then the new one, which has the horizontal shift, it's actually, if you notice, the one that started at 0 is now starting at -2. Here we had 8 as the original. The new one is at 6. Here we had 16, 17, probably 19. This one's now at 17. And then the original one here looks to be about 22 and is now at 20. No, it's at 24. Now it's at 22. Okay. Harder to see it with my printer. It's not as pretty as the one at school. Okay, so that just shows us that the original function was just called the new function g of t is equal to v of, instead of just t, we're going to have t minus, and they're moving it to the left, so -2. So that means that g of t is going to equal v of t plus 2. That is what a horizontal shift is going to look like based on what we've got here. And we'll call this one our g. Okay. All right. Notice that there's no k because there's no vertical shift. Moving up. Example 4, which is shifting a tabular function horizontally, dealing with the same numbers we had before, 2, 4, 6, 8, and the function f is giving us 1, 3, 7, 11. Now we have a new function g that is f of x minus 3. We know it's a horizontal function because it's not a k, it's not kicked out to another number to the side here. It's within the original function next to x. And if you'll remember, the new functions are equal to f of x minus h. So because this is negative, that means this 3 is actually h is equal to 3. So this is a positive 3. That means this would be shifting to the right because it is a positive 3. All right, you could plot these points as X's and Y's and see what's actually happening here to help you see the numbers as well. Okay. The thing with the horizontal shift or anything to do with the horizontal, anytime you change your horizontal of a function, you're going to have to change your initial X moving forward. You're going to have a lot of repetition down here, but the X is the one we're going to really focus on changing. Okay. So to get, one thing we can see from up here is that f of 2 is equal to 1. Okay. So now we have to change what's on the inside with this 2, because that's what's happening right here. All right. So if probably one of the easiest ways to do that is take that X minus 3 and make it equal to what's inside there. Okay. So then you could add 3 to both sides and you find out that X is actually 5. Hold on 1 second. Pause. All right, sorry about that. Like, so 3 plus 2 is 5. We got that. That's our new X. At f of 4, well, that's equal to 3. So if we want to, we can take X minus 3 is equal to 4, solve for X, and we get 7. This is probably easier than how I showed it before. For the next one, f of 6 is equal to 7. So X minus 3 is equal to 6. So our answer, next one's 9. And f of 8 is equal to 11. So X minus 3 is equal to 8. And that is 11 for our X's. All right. The next one we're going to do is when you have X minus 3, you're going to get the original X's back. So 5 minus 3 is 2, 7 minus 3 is 4, 9 minus 3 is 6, 11 minus 3 is 8. It's just the original X's back down here. But I also told you that the original independent variables do not change. The 2, 4, 6, 8s don't change. Well, actually it does. It changes from here to here. But the new X becomes the X minus 3. The old X becomes the X minus 3. And the new X's are going to be the ones that change. Okay, so now, if that's the case, then the new G of X is going to equal 1. 1, 3, 7, and 11, which was the original function. Okay, because f of 2 is 1, f of 4 is 3, f of 6 is 7, and f of 8 is 11. So that means that the new function, which is what they're telling us up here, G of X, is equal to the function f of X minus 3. So that means that whatever this function is, this one has to be 1, 3, 7, and 11. And so that's your final answer. Moving on. All right. Example 5. So this is not the original toolkit function of this quadratic, and I'll show you what that looks like. The original toolkit function, I'm just going to draw it in a different color, is a quadratic that 2 goes to 4 there, and it just keeps going, and this one keeps going. All right, so this is the original one. This is the f of X. Okay, and we have a new one, which is our G of X. This one's G of X. All right, so to find out what this new function is, we're going to write the formula for that. We need to see what is happening from the original toolkit function to the new one. Well, it's not shifting up, it's only shifting to the right. So this is just a horizontal shift. And remember, the horizontal shift is just the original function minus h. Okay, and this one, so this new one is f of X. It's moving over 2, so minus 2. The minus was already there. F of X minus is there. All we have to do now is plug in what X value that is, and it is 2. All right, so now we can do the final part of this, which is the X minus 2. but to put it in the same format as the toolkit function. So it needs to be represented with a square. Okay. If you're questioning this, put both of these in Desmos or in your calculator. Y equals x squared, y equals parentheses x minus 2 close parentheses square. And you will see that you will come up with both of these quadratics. All right. Interpreting horizontal versus vertical shift. So we're going to compare two different things here. We're given a function g of m that gives the number of gallons of gas required to drive m miles. So everything that I've told you is going to be covered on the exam, including this, is going to be. This part is not going to necessarily be covered on the exam. It will be in your homework. And you're going to need to interpret the difference between g of m plus 10 and g of m plus 10. So g of m plus 10, this is a vertical shift, okay? Whatever this function g is, so it's the number of gallons of gasoline required to drive m miles, the number of gallons is increasing by 10. So how would you write this? G of m equals 10. I would say that this is, they add 10 to the output of gallons. Okay, because this is a vertical shift. G of m plus 10 is a horizontal shift. And it's actually going to use less. So it's subtracting 10 from the miles. All right, from the original input, because this would be representing a G of m minus negative 10. Because remember, it would be x minus h. Well, so m minus, it'd have to be negative 10 to make us a plus. So that way it will tell you that this is going to be a negative. All right, just to understand what's happening there. Okay, 7. We're going to graph combined vertical and horizontal shifts using the, using the f of x is equal to the absolute value of x. This is all part of our toolkit functions. And we're going to sketch the graph, the new graph, the transformation that has us having a horizontal as well as a vertical shift. You need to understand that this part here is the vertical shift. And this piece here is the horizontal. Okay. And we're going to use x, absolute value of x, as our original function. So they're taking the original function and they're going to have a horizontal shift to it and then a vertical shift. So one of the things you need to understand is the original, bear with me. Probably should have had this already drawn, but I don't make the big bucks. Okay, there is your f of x is equal to the absolute value of x. There's your naming your babies. The new one is going to have a shift down and a shift to the left. So we're going to go to the left one, because if you think of the original, I showed you that it was f of x minus h. Well, to make a minus h, you would have to have f of x minus negative 1 to make this to be a plus, because this minus has to be here. I'm going to keep the minus 3. So we're going to shift to the left 1. We're going to shift to the negative 1, and to the right, I'm so sorry, and down 3. So from the original function, we're going to shift this piece right here. The whole stinking thing is going to shift to the left and down. So to this point would go to the left, and then 1, 2, 3. That is where that new point is. So now I can draw my new transformed function. Okay. And that is g of x is equal to. All right, well, what is that going to be equal to? So to put this in terms, the g of x is going to be equal to f, well, f is an absolute value of x plus 1. So x plus 1 minus 3. Okay, that's what this is going to have to use. All right, so this is absolute value of x plus 1 minus 3. If you have any questions, please make sure that you put those into your calculator or Desmos and see what it looks like. Let's go to example 8. All right, we're going to identify combined vertical and horizontal shifts, taking the toolkit function from the square root. Square root function is just y is equal to the square root of x, or it might say f of x is equal to the square root of x. We have a new one. Our new function is h of x that we're going to identify here. And we're going to have to see where this guy shifts. Well, we know it shifts up. The original looks like this. That's my best thing on that. So there's f of x is equal to the square root of x. And this one's going to be h of x. All right. From this point here, I'm just going to randomly choose a point that I can see. I know it goes through 0, 0. I can see that the new one is going to be going up 2 and over 1 for a point. So my vertical shift is positive 2. So I know right now my this is h. My h of x is going to take my f of x and add 2 to it. Okay. That's the first thing I see. The other thing I see is it also shifts from the y-axis over here to the positive 1. So that means now I've got h of x is equal to f of x minus, and then it's moving over 1. That's where I'm at for my vertical and horizontal shifting. So let's put this into what it's supposed to look like. Instead of square root of x, we're going to have that h of x is equal to the square root of x minus 1 plus 2. If you draw that in comparison to your f of x of equaling square root of x, you'll see that it has moved just like this one has up. Okay, moving to the next one. All right, now we're moving to reflections. So graphs functions using reflections about the axis. A vertical reflection reflects a graph vertically across the x-axis. So if this is our original function here, this one's our original, then our new one that is a vertical reflection is this one right here. This is a vertical reflection. Okay. It has to shift over the x-axis or shift down like that. It reflects a graph horizontally across vertically across the x-axis. Now, if we look at it a different way and just ignore this piece, let's go back to our original function. And now we're going to look at a horizontal reflection that reflects across the y-axis. And that one comes through and it's going to have the same height as the f of x as far as every point, but the x's are going to be different for horizontal. And that's what you see also when we do the tables, is the x's have to change. All right. All right, next victim. Let's talk about this reflection here. I usually like to, oh no, this one's fine. So this one here on example 9 will show you, given a function f of x, there's going to be a new function g of x that is negative of the original function. And it's a vertical reflection of the function f of x, sometimes called a reflection, over the x-axis. Okay. So that one's going to be g of x is equal to negative f of x. That's the vertical one. The horizontal one, given the same function f, there's a function g that it equals f of negative x. Now, that means it has to happen within inside the function. The x's themselves have to be negative what the original x's were. All right, but they're going to have the same y's. So let's look at this. This one we're looking at, this first two that we're looking at, the original function is this one. All right, and that is just s of t is equal to the square root of t. So if you put it into Desmos, your calculator, y equals the square root of x. It's just a toolkit function. All right. To see what the vertical one is happening, remember vertical flips over the x-axis. And so this is our new one down here. And this is going to be V of t. This is the vertical one. So V of t is going to equal square root of t. But what has to happen? For a vertical reflection, it has to be negative. So it has to be negative square root of t. So equals negative square root of t. So again, if you put in y equals square root of x and y equals negative square root of x, you will see the reflection that is vertical. Let's move up down to the next one. So that's a vertical reflection. Vertical reflection. The next one is going to be a horizontal reflection. Okay. The original one is here on the left. And this is back to our S of t is equal to the square root of t. And our new one, which is our horizontal of t, is equal to, well, if you're dealing with a horizontal reflection, please note the negative has to be inside of the original function. So it has to take the original function and the negative has to be inside because it's going to change the original independent variables. The t's, it changed from being at 1 to -1, from 2 to -2, 3. So it truly is a mirror image, is a reflection across the y-axis. All right, moving on. Back to tables. We're going to do a horizontal and a vertical reflection table to where we've got g of t is equal to negative f of x. That's going to be our vertical. And then h of x is equal to f of negative x, which is going to be our horizontal. So let's start off with our vertical flip first, vertical reflection first. And it will have, verticals have the same exact variables inputted. So this is our vertical. And what you do with this one is, how would I say this? G of x is equal to negative f of x. Okay. And what we could say then is, well, then that makes it negative f of whatever each of these values are. So negative f of 2 would be what? -1. All right, because f of 2 is currently 1. So negative f of 2 would be -1. So each one of these is just going to be the negative on the y values. Okay. For horizontal, we're going to have that h of x is equal to f of negative x. So h of x is equal to is equal to f of negative x. And that's equal to f of, well, -2. That means we have to change our x's because it's starting off with different x's. So it happens on the inside. So this becomes -2. It's negative x means we're going to have -4, -6, and -8. But the thing that's not going to change is the functions, is the y values. So even though the x's have changed, the y values will not change for horizontal changing. Okay, that's it for that one. Example 11. Now this one I did on Desmos, so bear with me. I'm going to pause for a minute and get switched over. Actually, I'm going to make another video. I'll see y'all back in a minute.